Greetings of the day. Welcome to the course on Operations Research Technique. In previous lectures, we have seen various aspects of linear programming. We have also discussed how to formulate linear mathematical model from given word problem. In last lecture, we have started with finding solutions to linear programming problem once it is formulated, and we have started with graphical solution. In graphical solution, what we did is we have solved one formulated problem by graphical method. So today, to begin with, we'll have recap of last problem and we'll find how to find graphical solution to other problems, other formulated version. So let's start with recap of the last lecture. So if you remember, in our last lecture, what we did is, this was the formulation, mathematical formulation for the given problem. So from the given data, we have this constraint equation 1, 2 with non-negativity condition, and we have identified various corner points through graph as A, B, C, D. Now in given problem, the objective function, original objective function was this. It was this objective function: maximize profit z equal to 6x1 plus 5x2. Rupees 6 was profit on 1 unit of pain, and rupees 5 was profit on 1 unit of beta pain. This was on 1 unit of alpha pain. So based on that, after getting the feasible region on the graph paper, which we have discussed in our earlier lecture, if I get this objective function and if I change the version of the objective function like this, you can identify in very clear manner the optimal solution and corresponding quantities of panes to be produced. Remember one thing, feasible region remains same, feasible corner points remain same. What I did is, I have changed to show how this changes. What I did is, I have only changed objective function. If this is the objective function, maximize z equal to 6x1 plus 5x2, you get these points, and for this is the maximum value. And here I have highlighted with blue color for feasible corner point C, value of x1 as 2, value of x2 as 3, and maximum profit which the organization will get is 27 rupees, which is suitable for this objective function. Means I have to select from so many answers of objective function maximize which is the maximum value. So here clear cut as highlighted by this blue color, maximum value is 27, and for 27 corresponding values of x1 are 2, corresponding values of x3 are 3. So answer will be, for this case, produce x1 units of alpha pain, quantity 2, produce x2 unit of beta pain, quantity 3 units with maximum profit, maximum z equal to 27. If you put these values in this equation, if we change this objective function right now, so for this objective function, for the same problem, your maximum value lies at corner point B, this one with yellow strip, and here what we can find is, this is highlighting produce x1 equal to 0, produce x2 equal to 5 to get maximum z to get maximum z of 30. So ultimately what we have to find from these values which we are getting from feasible corner points, which is the maximum value if our objective function is maximize z. Now in real life we may come across a situation where we will be having maximum value at more than one place. So it is called as multi-solution problem. I may get maximum value depending on the situation, which is 30 here at one place, I may get it at two places. So you have to keep in mind, and that is the special variety of linear programming problem where you are having more than one solution. The variety is called as multiple solution problem. Now we will try other problem. What I am doing now, I am keeping for understanding point of view this problem statement same, only I am changing objective function from maximize to minimize. What I am doing is I am changing objective function from maximize to minimize. I have changed from maximize to minimize. I have changed these signs. You can focus your attention on these signs. It is greater than equal to. In previous case the signs were less than equal to. Now we will do the same task which we did in last lecture. So here these are our x1 and x2 axis. If you recall our last discussion, this is the axis for x2, this is the axis for x1, and depending on the scale, now this is 1, 2, 3, this is 1, 2, 3, 4, 5, 6, 7. Again on this axis it is 1, 2, 3, 4, 5, 6 and 7. So as we did in last exercise, first we have to find the coordinates of these points. So coordinates will remain same. So what we did is put x2 equal to 0 for getting x1. If I put x2 equal to 0, I get x1 less than equal to 5, greater than equal to 5. So first coordinate is 5, 0. And if I put x1 equal to 0, x2 is greater than equal to 5. So this is the first coordinate. We have already seen in previous lecture how to obtain this value in the same manner. For this, again, if we put this 0, x2 equal to 0, we will get 3x1 greater than equal to 12. So x1 greater than equal to 4. So first quadrant would be point will be 4, 0, and second, if you put this equal to 0, you will get 2x2 greater than 12. So x2 greater than equal to 6. So this we have already studied in our previous points. So remember the points now. It is 5, 0, 0, 5, 4, 0 and 0, 6. Now our task is to define scale. So as we did in previous scale, here scale it will be same. So here now 2 centimeter is equal to 1 unit, and it is on both axes, scale on both axes. I have selected the scale. This 2 centimeter distance is equal to 1 unit. Now what we will do? We will draw these lines. First line x1, x2 greater than equal to 5. So I have to mark this point 5. This one, join by straight line. This is first line which is representing x1 plus x2 greater than equal to 5. Now this sign, importance of this sign, it should be understood again. The value of maximum value of x1 which this equation will give you is minimum is 5, other values greater than 5. Similarly for x2, minimum value will be 5, and to indicate that minimum value is 5, I have to give direction like this. If you recall, in last problem of maximization, we have arrow in opposite direction to satisfy that particular condition. So hope this is clear. Now we'll see, plot another point. Another point is, this is, another point is 4, 0 and 0, 6. So this one. Now again you have to draw a straight line. Like this. Here 3x1, if we put this equal to 0, 3x1 greater than equal to 12, x1 greater than equal to 4. That is, the values of x1 on x1 axis for this line are greater than equal to 4. So I am drawing arrow indicating in upward direction. Same is the case, 2x2 greater than equal to 12, means x1 can have value minimum 6. So this is minimum 6 for x2. Other values may be greater than 6. To indicate that, we are plotting, marking this upward direction, and this line is represented as 3x1 plus 2x2 greater than equal to 12. So now it is very clear. We have drawn both lines which represent our objective function, these lines. Now, as we did in previous case, these are the simultaneous equation. This condition, minimize total cost Z, will be achieved only if these two constraints are simultaneously achieved, simultaneously followed. So it is not that only one constraint will do. Again, recalling the last problem discussion, considering this area shown by these arrows, for this line, this particular area is not suitable. For this line, this particular area is not suitable. So what we have to do? We have to find the feasible region which both lines satisfy. So if you look at this particular region with respect to xy, that is very important, with respect to xy is the only feasible region. The meaning of feasible region, as explained in last lecture, is our solution now. Our solution to this problem lies in this region. There is no scope of our solution lying in this region. Now, region is identified, but the condition is now minimize. So you have to be alert. Again, what we have to do is, we have to identify the coordinates of feasible region, coordinates of this feasible region which satisfies constraint equation and optimizes the minimize function. So what I will do, suppose this point which is intersecting with x2, I mark this point as A, I mark this point as this particular point this particular point as A. Now for A, it is x1 is 0 and x2 is 6. A is identified. Other point is this one is B. So if you draw it correctly, again you will get the intersection point as we did in last lecture is 2, 3. 2x1 and 3x2, and here this, if I say this as C point, so x1 for C is 5, x1 for C is 5, this point, and value of x2 for this C point is 0. So in earlier case what we got is 4 feasible corner point. Now for these constraints with minimize, I got feasible corner point A with x1 0, x2 6. This is 6. Second feasible corner point B with x2 2, 3, and last I got C point as 5 and 0. So what we did till now is we have identified feasible corner points. Now we will calculate the value. Here the value is, suppose, again we will change this, we will go for by original one. It is say suppose 6x1 plus 5x2, original problem, or we can also go with the same, no, there is no harm if I continue the same value of x1 and x2. So I have to write here 5x1, I have to write here 5x1 plus 6x2. But now here I have to calculate for minimum, so I will erase this maximum. So my target here is minimize. So what I am doing? Minimize 2x1 plus 6x2. Simply you have to put the values. 5 into 0, 5, if I put it 5 into 0 plus 6 into 6. So this comes out to be 0 and 6 are 36. Similarly for this, it will come out to be 2 5s are 10 plus 6 3s are 18. 2 5s are 10, 6 3s are 18. So this turns out to be 28. And last 5 5s are 25. 5 5s are 25. 6 into 0 is 0. So 25. So from these values of objective function, all these z values, if we compare, we find minimum value is 25. So answer for this problem by graphical method will be produce answer for this problem by graphical method will be, now produce x1 equal to 5, x2 equal to 0, and your total cost minimize z will be equal to 25. How you arrived at this point is through comparison of these values of objective function minimize z. So this is the problem wherein we have studied how to find graphical solution. Now one thing you have to keep in mind, graphical solution is only applicable if and only if there are two variables. For more than two variable, we have to go for analytical treatment, that is simplex method and big M method, which we will be studying in coming lectures. Now our focus right now is on two variable problem, graphical method. These problems can also be solved by analytical method, that is by simplex method or big M method. Answer will be same if you attempt it by graphical method or by simplex method. So now we'll go for next problem, graphical solution. Now again, in this third problem, you can see the constraints. I am changing the constraints, and that we have to study. What I am doing is I am changing the constraint. Objective function is I have kept same, minimize. What I did is now I have added one constraint with, this is very important, I have added one constraint with equal to sign. This constraint I have mentioned as less than equal to 4, and this constraint is greater than equal to 4. How to draw these lines? For this we have studied many a times. So it will be 5, 0 and 0, 5. For this it is obvious, for this it is obvious that it will be 4, 0, and for this it will be 5, 0, 5, 0, 5. Now we have to identify. Basically what we can do is, suppose we don't put it like this. Only I have shown this for understanding what is the value of x1 and what is the value of x2. So now what we'll do, we'll select again the graph. Say we'll select two axes again. This is axis x2, this is axis x1. Now for clear cut understanding, again we are keeping the distance 1, 2, 3, 4, 5, 6, 7, like that. On this axis also 1, 2, 3, 4, 5, 6, 7. The maximum I know it is less than equal to 5. So I am giving up to 7. Now I have to write scale here. Scale on both axes. I am writing, since it is same I can write both axes, or you can mention separately 2 centimeter is equal to 1 unit. Say this is 2 centimeter. 1, 2 centimeter is equal to 1 unit, same on y-axis. Now what we'll do? We'll plot the line. First line x1, this is 5, 0, 0, 5. So this is the point, and another point is this point. So I have to join like this, and here I have to write equation of this x1 plus x2 equal to 5. Now one thing you have to remember, very very important, whenever there is equal to sign on the line, you cannot mark the area representing like this by arrow, because it is specifying the condition, the value of x1, if you put x2 0, is only equal to 5. Value of x1 is only equal to 5. Similarly, value of x2, if you put x1 is 0, only equal to 5. So there is no marking of arrows. Those we did in earlier 2 examples. That is very important for constraint whenever it is equal to. Now we'll plot this second line. For plotting this second line, x1, this is x1 and I have written earlier it is 4 0. So x1 line will pass through this, it will pass through this. Now value of x1 maximum is 4 and less than equal to 4. So here what I will do, I will mark this by arrow like this. Got it? For this equation equal to no marking by arrows. Now since it is less than, I did this. Here I will write the equation for this line. It is represented as x1 less than equal to 4. Second line. Now let's draw third line. x2. x2 greater than equal to 5. So for this your point will be 0 5. So this is 0 5 point. So a line parallel to x-axis, a line parallel to x-axis representing x2 greater than equal to 5. Now since the value of x2 maximum can be 5 and remaining values greater than 5, so I am marking arrows like this. I am marking arrows like this. Now very important again, one thing you have to keep in mind, you have to achieve this objective function. In earlier 2 cases there were only 2 simultaneous equations. Now in this case you are having 3 simultaneous equations. This is first one, this is second one, this is third. This is non-negativity condition. This minimized objective function will be achieved only if these 3 constraints are simultaneously obeyed. What you have to keep in mind is your solution, whenever there is mixed constraint and one of the constraint is equal to type, you have to keep in mind that your solution to the problem will always lie on equal to line, because this is one of the constraint. Solution will lie on equal to line satisfying other 2 conditions. So first identify which are the points on equal to line which satisfy both the condition. So students, if you see here, this is our equal to line. For this we know now our solution will lie only on this line. If I consider this point, this point lies on this line, this point lies on this line, and this point also satisfied the area left to this line, x1 less than equal to 4. Suppose I write this as point A, which is 0 5. Other point is this, but see, this particular point is not taking care of this line. This is taking care of only this equal to line and this line. So this point is out of question. Since area above this 5 will be considered for this constraint, so only you are having only unique answer, which is point A here, which gives you the value of, because because this particular point lies on equal to line 1. It satisfies this condition of x1 less than 4. It also satisfies this condition of x2 greater than equal to 5. Only unique point A. So the meaning here, answer for this will be only one point you are getting with x1 quantity 0, this quantity 5, and here as you can note it is your objective function is minimize. So equation is 5x1 plus 8x2. Answer for this is 5 into 0 is 5. 8 5s are 40. So answer for this problem with minimize is 40. What is the important thing? Solution lies on equal to line. That you have to remember. Your solution lies on equal to line. Now, suppose other conditions being same for the constraint, if I only change this objective function from minimize to maximize, what will happen? Is this entire scene or whatever drawn on graph is going to change if I change the objective function from minimize to maximize? Definitely no, because I am not changing constraints. Constraints are same. What I did is only objective function I am changing from minimize to maximize. This will remain same, point will remain same. There is one only unique answer 40, so the same answer will be for maximize. Now in these cases, whenever you are having more than one point, say 2 3 points, so for minimize you will select minimum value amongst the available feasible points solution, or if you are having maximum objective function, select maximum value for these feasible corner points from amongst feasible corner points. So in case of minimum we will select minimum, in case of maximum we will select maximum. But what you have to remember in mind is that your solution will lie only on this equal to line. I think it is clear now how to tackle when it is equal to. Now we will go again ahead of. Now here I have kept this graph to explain the concepts wherein suppose I get the situation like suppose I plot this axis, this is axis, this is axis, I label this axis as x1, I label this axis as x2. Now what I will do, we have studied formulation. What I will do, I will only draw the lines, hypothetically I will draw the lines, and I will try to explain what will be the solution if we come across such situation. In earlier case we have seen that if it is equal to sign, our solution lies on equal to line satisfying other condition that we have studied. Now what I am emphasizing is, suppose I get this one line with equal to constraint, I get this one line again with equal to constraint. See, I have changed the definition. Now objective function may be for this situation maximize or objective function may be minimize for this given situation. What I am trying to explain now, suppose we come across with constraints with equal to sign, both constraints equal to sign. So definitely we can find the points. After finding coordinates, we will plot the points. And if you come across, see here, I have not shown any arrow. I have not shown any arrow because there is no need to show any arrow since it is equal to. Since it is equal to means it is satisfying. This point, this point, this is one point, this is one point. The maximum value will be those 4 points. Question is, what about solution in this case? Very important. Whenever let it be any objective function, maximize or minimize, if you are having only 2 constraints in a problem with sign equal to, my stress is on with sign equal to. What about solution that I am stressing? So solution will be blindly unique solution. It is point of intersection of 2 lines. This is very important. This point, project it down, project it left. If I project it left, I will get this point. Coordinates, I will get x1 coordinate for this point, I will get x2 coordinate for this point. Clear? Whatever the point of intersection you are getting when equal to sign is there, your solution will be always point of intersection of these 2 lines. That you have to keep in mind. Now what will be objective function? Depending on whether it is maximize or minimize. Suppose the equation is maximize 3x1 plus 5x2. We'll put those values of x1 and x2 here. We'll find maximum value. If objective function is minimize 3x1 plus 5x2, again what we'll do, we'll put these values here and we'll find the value of maximize or minimize. I think it is clear. Now what we did, we have seen the cases wherein all constraints were less than equal to type. First case, if you recall, all constraints were less than equal to type. In second example, I have covered all constraints greater than equal to sign. In third, what we did, this is our first example case, this is our second example case. In third case, what we did, we were having equal to, greater than equal to and less than equal to. Now in this latest problem, what as a fourth case, what we have seen, only, I am stressing, only equal to constraint, only equal to constraint. And whenever there is only equal to constraint, remember one thing, your solution will lie on point of intersection of both the lines, satisfying your objective function. Clear? Now we'll go ahead. See here, Suppose I get for a problem formulated version as this one, as given in this problem. This is formulated version, and in that formulated version objective function was to minimize z, that is given with, this is first constraint, x1 plus x2 greater than equal to 200. See here, the constraint here is greater than equal to. Second constraint, this is the values which we get from wording problem. Converting in appropriate form, you get this equation where again it is greater than equal to form. And third constraint, it is less than equal to form. So this is fifth variety of problem. We have seen 4 varieties earlier. All constraint less than. Second variety, all constraints greater than. Third variety, mixed constraint, less than equal to, greater than equal to. Fourth constraints, fourth category of problem we have seen where the constraints are equal to. Fifth variety, where constraints are greater than equal to and less than equal to. How to proceed? How to find the solution graphically for this case? Now here there is no equal to line. So there is no question of solution line on equal to line. I think it is very clear now. If there is equal to sign on any line, then only solution will be on equal to line. Else in all cases other than pure equal to constraint or mixed equal to constraint, other than these two cases, you will always have feasible region representing your solution area. Feasible region representing your solution area only in case of equal to. Whenever there is equal to, you will have the point indicating solution lying on equal to line. That you have to keep in mind. Clear? Let's move ahead. So these are the constraints with objective function minimize. This is objective function, this is first constraint, this is second constraint, and this is third constraint. Now we will see how to tackle such problem and how to interpret the result of the problem, and I will also explain what will happen if I change this. If I change this minimize to maximize, suppose I change it to. Right now we will see for minimization. I will explain what will be the solution if it is maximization. Let's move ahead. See here, I have drawn this solution directly now. It is proportionate. Instead of drawing on graph paper, I have taken a proportionate scale on x1 axis, x2 axis, and first line. Now here first line, our first line, for drawing these lines we are writing it equal to 0, but the line is representing as, if you recall, for first it is greater than, not less than. For first it was greater than, for second it was also greater than, for this it was less than. here the sign was, this is correct for finding the values. Now to understand, I will explain here like this. So here we know that if I put x1 0, x2 0, x1 equal to 200, put x1 0, x2 equal to 0, coordinates will be 200 0 0 200. So you can find this is the point. Now as per our earlier practice, for this one, this will be the region, feasible point region. For second, this is the line which is represented by this second. Coordinates you find, sign is greater than equal to, so region will be like this. Now important, for third case our sign is less than equal to, this is the equation pertaining to third case. So if I extend this, so here the arrow sign is like this. Now what you have to do? What we will do? See, this region is not permitted. This is only satisfied by this line and this line, but not by this second line. So this is out of question. Similarly, for these two regions with respect to x1 and x2 axis, these regions are out of question. This region is also out of question because this second constraint is not considering. So in such cases, whenever you are having only combination of less than equal to and equal to, you have to find the entrapped area which is justifying the constraint signs for both resources or for number of resources in the problem. So now you can see here very well, this particular is the entrapped area which is called as feasible region, and this particular region which is highlighted by point A, B and C are, this is I am marking for understanding purpose. This is the area where our solution lies. Area confined by the points A, B, C. So what is our task? We have to find the coordinates for A, we have to find the coordinates for B, we have to find the coordinates for C. So if you drop it perpendicular correct on this particular graph, I did it on graph paper, actual graph paper, and then based on that graph paper I have plotted this chart. So here the value which I got by drawing on graph paper, because here if you find it, since it is not a graph, you will not get exact value. So value of A is 100, that is x1 100, x2 100. Value of B is x1 250, x1 approximately you can see here. If you drop perpendicular from this, you will get ahead of 240 is 250 and parallel 40 and 80 near about a point 50. Similarly, for C, your x1 coordinate is 50 and x2 coordinate is 150. So these are the three feasible corner points now for this feasible region, where area is entrapped by these two constraints, less than equal to and greater than equal to. Clear? Again, what we'll do, we'll make tabular representation. We'll find the values. What we did, as we did in previous cases, same. Extreme points, feasible points, coordinates for those points, and these are the values to be computed from objective function minimize. That is given in the problem. So now you know how to find these answers. I have explained it 5 times in earlier problems. So you get 3 values for feasible corner point A, B, C. If your objective function is minimum, as the case here is, amongst these find the minimum value. So now the minimum Z is defined, which is rupees 60,000. Project this 100. So values of your x1 will be equal to 100 units. Value of x2 is also equal to 100 units for objective function minimize. For objective function minimize, the value of x1 and x2 are 100 and 100 with z 60,000. With z 60,000. Now suppose, this is very important, suppose for the same scenario I am keeping the constraint equation same, but I am changing objective function from minimize to maximize. Only this simple change suppose I am doing in this problem, constraint equation same, and only change in objective function from minimize to maximize. Listen one thing, when you are not disturbing constraint equation, graph will be same. Graphical feasible region identified will also be same. So for this case, whatever region we have marked in last slide, same will be the region and same will be the points. ABC points will be same, even if I change only objective function from minimize to maximize. I have not disturbed, mind well what I am stressing, I have not disturbed constraint equation. So in this case, what I have to do, how to interpret maximize answer, I have to check these values. Here the values you can find is 60,000, 70,000, 70,000. Now remember here, if it is maximize, you are getting these values, maximum values as 2 places. Yes, that is possible in real life. I have explained in the beginning, very beginning, such problems are called as multiple solution problem. Means for attaining the same objective function, you are having 2 ways here as mentioned. One is your maximum value of, suppose it is what we are saying, suppose it is maximize. First way is your value of x1 will be equal to 250. Your value of x2 will be equal to 50, and maximum z will be equal to 70,000. This is first solution. What is second solution? Second solution is this one, that produce x1 equal to 50, x2 equal to 150, max z equal to how much? 70,000. So students, this is very important that for the same problem you may have more than one solution depending on the objective function asked. For this problem, if objective function is minimized, there is only single solution. But for the same problem, if objective function I change from minimize to maximize, I get two answers for that maximize problem. Both answers are correct. Only the values of x1 and x2 are changing with final value of max z remaining same. So these are cases in real life. Now we'll see what are the other cases, how we tackle critical cases in linear programming graphical solution. So see, this is some special cases which you are getting. Now depending on the solution, see here for this problem, this is identified as feasible region. This is identified as feasible region. Now if objective function here is maximize, if objective function for this case is maximize, your answer will be at some infinity. It will be maximum answer will be at some infinity, farthest distance you cannot reach. The meaning interpretation of such cases is problem has an unbounded solution. Problem has an unbounded solution. That the meaning, enjoy in market the maximum profit which you can enjoy. Produce as much as you can. Lot of customers are available. Your product will be sold in the market. So there is no limitation if you are getting condition like this for maximization, unbounded solution. No restriction on the profit value. Reverse to this, focus on this. Reverse to this, focus on this. Now, what we can see here? That if this is the line, this line shows feasible region over here. This line shows feasible region over here. Two lines which are to be simultaneously achieved are showing different feasible region. That is very important. There is no commonness. There is no association between these two lines to represent a common feasible region. If you come across this situation in real life, problem is stated or interfered as it is having infeasible solution. Unbounded solution, second case, infeasible solution. Same. Infeasible solution, it is again in upward direction. This is your feasible region. This is in lower direction, feasible region. No agreement between these two lines to justify the common area, ending with infeasible solution. And last, if you come to this case, four lines, four constraints are there. One constraint is showing this area, other constraint is showing this area, third constraint is showing this area, and constraints are not satisfying individual area shown by the lines, and therefore you cannot get confined feasible region, and therefore no feasible points, resulting towards infeasible solution. So we have started with linear programming, OR rather, definition of OR. What is linear programming? How to formulate problem from given linear programming. We have practiced how to formulate the given problem from the word data. Then we have started with finding solution to the linear programming problem. We have stated two methods. First is graphical, second is analytical, that is simplex method. And we have seen how graphically you can attempt solution of linear programming problem. So this particular topic covers entire graphical solution to linear programming problem. So here we will end our discussion on finding graphical solution to linear programming problem. From next lecture we will start with analytical solution, and that is simplex method. Till then, practice these problems from the taught course material.